Ooh. Hmm. Okay, the mic is accidentally turned on, so there's no battery. So I have to shout again. If you cannot hear me, please ask me. Please tell me from the back. If you cannot hear me, please let me know. Because my battery is dead for mic. Okay. So before we start, we got a bunch of questions from you, some of you. So let's discuss the question first. Okay. First question is about this example in the lecture note. So we discussed about the column space and row space before. Okay, so let's look at this question again. So we are trying to find a basis for the column space and row space of this matrix here. Okay, so before you find this basis, right, you have to know what's the meaning of this three word. What's the basis? Okay, what's the basis? What's the column space? What's the row space? Okay, so what's basis? Set of vectors that span a sub and linearly independent. Okay, span a subspace and they are linearly independent. So what's the subspace we consider here? So one is column space, one is row space. Okay, so column space definition is what? So the keyword here is span. Okay, co A equals to span of some column vector. So what are the column vector here? So basically you need to split your A into column. Okay, and there are 5 of them here. Okay, so it's a span of 5 vector here. Okay, so again, recall what's the definition of span? Is so the keyword is what? Linear combination. Okay, so all the elements here are linear combination of these 5 vector here. Linear combination means what? Scalar, multiple, and sum. Okay, any scalar, multiple, and sum. How about row space? Okay, row here refers to what? The rows of the matrix. So you need to split your matrix into row. Okay, so there's a very fun observation here. When you split your column, your matrix into column, then your A will be labeled horizontally. But when you split your matrix into row, your label will go vertically. Okay, so this is something to note here. Row space is what? Row space is then the span of the row vector here. Okay, so we have shown that span of any vector is a subspace. So we can find the basis for a subspace. Okay, so many people ask me geometrically how you think about basis. So subspace you should think about a space. Okay, if I mean some of you say that column space is a space, then must be geometry, right? Yeah, you are true. You are true. But depend on what's the dimension. Okay, if the dimension is more than 4, we cannot draw it. So in general, you just think of a subspace as some ball like that. Okay, and then how to look for this basis? So basis is something inside here. Okay, that are linearly independent and span. Okay, maybe still a bit hard to imagine. Let's draw some real geometry here. Let's give an example. Maybe this is a plane. Okay, plane is a subspace. So if it contains the zero vector here. So what's the basis here? So what do you look for in your plane? Actually, the basis vector they are looking for is two linearly independent vector that spans your plane. Okay. So meaning what? You can build this plane using these two vector. Okay. Yeah, these two vector here. Yeah, no? Can you imagine you can build this plane using these two vector? Before building the plane, right? You should think that you can build the cross first. Or not, because you can scale the line anywhere you like. Any C, right? Any C times V must be live in there. And then how to create the first quadrant, second quadrant, and third quadrant here. You need to add up all the possible sum. Okay, so that you can get all these points, right? Okay. Remember that adding two sum together is like a parallelogram rules, right? So you can get all the points inside this quadrant by using this vector coming from the cross. Okay. Yeah, so this is two-dimensional. You can really draw two-dimensional, three-dimensional, four-dimensional, you cannot draw already. Okay, so meaning if we look at span of four linearly independent vector, you can't really draw it already. Okay, three-dimensional, two-dimensional, one-dimensional, you still can see the line, plane, or a cube, maybe. Okay. Okay, so this is about the geometry. And right. So how to find basis? Last time we have a theorem, right? Basis of co-A. How to find basis of co-A? Or the pivot column. Okay, coming from the pivot column, not the pivot column itself. They are not equivalent. You have to pick from the original original matrix. Okay, you need to pick from the original matrix. So, okay, maybe this one is quite trivial. This is already REF form. Maybe we do one example then. Oh, I got this. This is not, okay. Later I'll explain this. This is not a very good annotation. I'll change it. Okay, let's do one quick example first. Let's not use the REF form. So let's say we do a very simple one. One, 0, 1, 1, 2, 1 like that. Okay. Okay, let's call this A. Okay, so now we want to find basis for co-A. Okay. Find basis of co-A. So okay, let's change this question a bit. Change to 2, 1, 1 like this. 1, 1, 2, 2, 1, 1. Okay, so the theorem is theorem pivot. Okay, so should write like this. The column of A that correspond to the pivot column of the RREF form of A are the basis for OA. Okay, so this is a theorem. It's not hard to prove also, but we won't talk about it. So to do this, we need to row reduce. So we need to row reduce our matrix. Okay, so if you row reduce this, Let's quickly row reduce this. So 0, -1, -3. Okay, so you can see that these two are the pivot column. Okay, so we will say that basis for col A is equals to the column 1, 2, and 1, 1. Okay, note that. So here I want to warn you. Warning. Okay, we are not picking 1, 0, and 1, 1 minus 1. Okay, we are not doing that. Okay, often student will just pick this pivot column as your basis. It is not. Okay, because these two, the space that's spanned by these two set of vector might not be the same. Yeah. Does it make sense? You need to go back to your original matrix and then pick up the column. Okay, you cannot pick the one that is row reduced. Okay, they are not equivalent. The subspace might not be equivalent. Okay, does it make sense? Okay, but there is another question about row space, right? But how do you find a row space? Row space is the same. You pick the row that contain the pivot. Okay, you pick the row that contain the pivot. Okay, so let's say, so second part. Find basis for row A. Okay, so we can see that from REF of A. Okay, REF. EF already got form, right? Okay, no need form. We see that basis for row A is what? The both row. Okay, both row is your basis. 1, 1, 2, and 2, 1, 1. Okay, but for row it's a bit special. You can take the row vector coming from your REF. You can do this. Why? Why can you do this? You can do it for row. Why? Equation can do multiple, not quite around there, not quite. How you when you do REF, what do you do? You take linear combination of rows, right? So actually you are playing around with the span of the row already. Already you are playing around with the span of the row. Okay, so the span is the same. Okay, but how do you see linear independent here? Okay, from here, how do you see they are linearly independent? Can you see that after you row reduce, right? You cannot actually get this one from the other vector, actually. Cannot. No. So no matter what scalar you multiply to the other vector, you cannot get one in the first spot. Okay. So these two are linearly independent. Cannot. Okay. So we see linearly independent for rows because when you build this pivot thingy, right, you'll see that you have like 0, okay, getting more 0 under the pivots. And then these 0 cannot create pivots anymore. So they are linearly independent. Can you imagine? Okay, so I mean, maybe this one a bit small. This one a bit small. Let me give you a bigger picture here. Let me give you a bigger picture. So 1, 0, 1, 0, 0, 1, 1, 1, and then maybe 0, 0, 2, 1 like that. Okay. So let's say we want to find, let's call this B. Find the basis for row B. Okay, so what's the basis here? So it is actually, so let's say call it beta here. So beta is equals to 1, 0, 1, 0, 0, 1, 1, 1, and 0, 0, 2, 1. Okay. So you can easily see that there's no non-trivial relation between these three. Right? Because no matter what you multiply to 1, and no matter what you multiply to 0, they cannot equal 1. First spot already cannot equal. How do you get all the number equal? Does it make sense or not? Does it make sense? Yeah. And then also, how about the second spot here? How about second spot here? Yeah, so you cannot make this 0. Yeah, yeah. Okay. Yeah. I want to keep it there first. Okay. Any question? Any question? So for so the moral is for your column space, you need to pick from the original column. For row space, you can pick from the row reduced form. Okay. Both of them, go and look for your pivot first. So you can call one of them is pivot column, the other is pivot rows, if you like. Rows that contain the pivot. And then I think in my note, I wrote something like this as my solution. This one is from last year, but this year I didn't do this, right? So I think I will change this notation here. I won't write this, I won't write this, I won't write this kind of thing, so I want to make it clear here first. So what I will write is, so in this course, right, what are equivalent? So either I will write like this, A1, A2 up to AN, or I will write like this, bracket, round bracket, A1, comma, A2, comma, okay? So if I write like the other way, right, A1, A2, AN, right, this is a 1 times n matrix. Okay, usually the vector in Rn, I will write it as n times 1 matrix. Okay, so this 1 times n is just a matrix, not a Rn element. Okay, so these are two different things. So I don't want to make it equal now. I mean, in this course, I will adjust this writing because this one for last year. Can or not? Understand? Any question? So frequently, you will see me using this tool. Actually, there's a reason one. Why sometimes I bracket, sometimes square bracket. There's a reason one. You want to guess what's the reason? If you learn more maths before, based on your understanding. There's a reason one why we write like this, although they refer to the same point in the space. Okay, usually when we do this square bracket thingy, right, we refer it as a vector. There's a magnitude and scalar. But when we refer to this kind of round bracket, right, we refer to that point. Does that make sense? That's a coordinate. It's a coordinate. Okay. But every coordinate, right? So every coordinate in your XY plane, for example, actually it is a vector coming from the origin. Yeah. So this vector usually we will write like this. Okay, can understand? Actually, they are the same thing, but one usually we use it for coordinate, the other use it for that has a length and magnitude. So you have a length here and then the direction. Direction and magnitude. They are the same thing. Okay. Okay, so this is about basis. Yeah, so basis is important. So this Friday quiz, you will get question like that. Okay, make sure you know how to find basis. Right. So one of you post in the forum, right? Oh, what's the name? Anyone read the forum? Moodle's forum. Did you know someone post something here there? Have you checked it out? Inside the student forum. Xingyu, did you post something there on the Moodle forum? Yeah. So are you supposed to get help from them or me? Anyone or anyone can help. Huh? Did you understand what I say? You understand what I say or not? Yeah. Okay. So are you trying to get help from them or me or anyone? Huh? You just want to ask, no need help one, huh? Xingyu, you understand what I said or not? Can you answer me? Huh? What's the purpose you post there?哦，你现在搞明白了。没有，当初你是要跟他们想问他们，还是问我，还是都可以，大家都可以问。哦，都可以哈。OK，好。Yeah. So since you already 搞懂 right, can you tell us what you know, what you learn? 看到你有一点可怜哦，没有人回复你耶。不然你跟我们讲一下你学了什么？你说说看，我帮你翻译。来，赶紧，说说看。啊，你没有，对啊，是啊，我知道你没有问题啊，我是说你学了什么，所以你问题怎么被解决的？告诉我们一下。你知道我们在说什么吗？静宇，OK。所以你问为什么那里没有一个 summation 是吗？所以为什么没有啊？Ah, right. So yeah, correct. So we expand across first column. Yeah. So in the okay, I think if everyone have the Moodle forum question here. So he asked why there's no summation here. You're supposed to add a lot of thing together, right? But the thing after the first row, first column actually are all zero actually. Yeah, yeah. Okay. 你怎么搞懂了？Ah, okay. Yeah. Yeah, so he said he looked at a lot of similar question. So that's why I asked you to do tutorial question so you can learn. Okay, don't start on one question. Yeah, very good. Yeah. So feel free to pause here. If you have any problem, you can pause here. So this one is under student forum, right? So any one of you can reply one. As long as you think you can help, you just help him. Even if you screw him out, also can. Okay, so learn together. Try to learn together. Okay, yeah. Okay. Other than this, you have any question or not? Any question other than this? Yes. Is the column space unique? You mean if you fix an A and then you find a span, is it? Yes, it is. by definition, yes. Same. All right. So yeah, I thought I said this idea before. So different subspace. Okay. So different subspace could have different bases, but different bases to give you a same subspace. Yeah. So in our case here, oh yeah, okay, yeah, okay, that's all. I think that's all. So usually there's one thing I want you to notice here. Usually, right, row space and column space live in different space. Correct or not? Because okay, sorry, I should remove it. Because you see, where does this row space live? Row vector live in R how many? Which Rn? R5, right? But columns vector live in R4, different space. Okay, different space. Okay, usually column space and row space is a different space. Okay. Any other question? Okay, if no question, today we will give back your quiz and then we'll discuss. Okay, when you get your quiz right, later you can take a photo because you will need to return your quiz to me. Okay, I need to keep a record. So when we discuss, when the class get boring, I'll start discussing quiz. Okay. Okay, so let's continue with vector space chapter. Okay, so let's tell the whole story again. So let's recall. So the first story to tell is about vector space. So we start with a vector space. Yes, you think as a space as a geometry is very true. For example, the space we live in now, okay, the physicists will model this as a vector space. Okay. Or if you look at some scientific article, they call it a Hilbert space. Okay, so what's a Hilbert space? Is a vector space with inner product. Later we will learn about inner product. Okay, this is to measure the length and then the angle between two vector. We will do it later. So what's the vector space? First of all, it is a set. Okay, it's a set. Okay. I mean, set come with elements. No? And then there are two operations. With two operations. One is addition. You know how to add two things together. And then the other is called scalar multiplication. Okay, so there's a very good reason why we don't call it a multiplication instead of scalar multiplication. Meaning what? We cannot multiply two vector elements together. No, there's no v1 times v2. No, but we know how to multiply with a number, a scalar. Okay, that's what we know. So if I want to record these two, maybe I write v1 plus v2 and then cv1 like that. Okay, this is the two things we can do. Okay, we cannot do something like v1 times v2. Okay, not like this. Although later course we will learn how to define product between two vector. And then the other one is 10 axioms. Okay, you need to check all the 10 axioms. Okay. And then inside this vector space, there's very interesting stuff to study, which is called a subspace. Okay. So subspace is what? So let's call this vector space V. Let's call vector space H. This is a subset. Okay, so it's a subset. Okay. And then come with three conditions. So there are three conditions here. One is the zero vector must live in H. Second one is closed under addition. And then third one is closed under scalar multiplication. Okay, closed meaning if you take two things inside the subspace, you do the operation, it still live inside the subspace. You don't go out from the subspace. Okay, you stay inside the subspace. And some of you ask me, in my note, I actually check 4 conditions. So this subset is like the 0th condition. Okay. If it is not subset, they are not subspace of each other. Maybe it's a vector space. So for example, I'll say that R2, right, is not a subspace of R3. Why? Why is it not a subspace of R3? It's not even a subset. Inside R2 looks like what? XY. Inside R3 looks like what? XYZ. It's different. But you ask me, oh, can I borrow a paper? So maybe you think that, oh, this is R2, right? Hey, isn't it R2 live in R3? Our space is R3. Isn't R2 live in R3? Say yes. Who? Rami. Can you say yes? It's okay. Be brave. Okay. So how do we see this phenomenon actually? So actually, what you see is what you see is we try to embed. Okay, we embed this scientific term we call embedding. So we embed. I'll let you know what is embedding. So embed this xy into, for example, xy0 like that. For example, okay, I put in. Okay, let's draw this. So let's say R2 looks like this, a plane, right? So how to put R2 inside R3? So maybe you put it as a XY plane here. Okay. And this is not the only way, right? Not the only way you can put it in. Right. There's a different level, right? You can put this high. You also can put this high. So meaning what? You can change the height also. Okay. You can change the height also. Okay, I don't want to write equal here. So okay, so there are different ways the plane can sit inside R3. Okay. But once it is in R3, you need to write it with 3 components. Okay. But R2 and R3 itself, they are not subset of each other. Okay, not the same. Does that make sense? Okay. So when you see R2 in R3, actually you do this embedding already. You put in an extra component. Does it make sense? Okay. What else? Yeah. Okay. So, okay, let's use this picture then. Okay, so we have a vector space which is R3, and then we look at the XY plane as your subspace. Okay, so this is our subspace. So how to look for basis? So the next part is look for basis. Okay, how to look for basis? So basis is a set of vectors that span. So span who? So you need to say find basis for who first. Okay, basis of H. Okay, must span H, and then they are linearly independent. All right, so in this case here, you go into this plane, find 2 linearly independent vector. Okay, from here, you can deduce the dimension of H. Okay, so the dimension of H is what? Number of vectors in the basis. So let's call this basis B. Okay, let's call this basis B. Okay, so in this case here, you have 2 linearly independent and spanning vectors. So there are 2 of them. So dimension of this plane is 2. So that's why you say R2 is dimension 2. Okay. Yeah. Can follow? Any question? Okay, so why are we abstracting these ideas? So last time I show you examples, right? So let's go to the examples. Why are we doing these? Okay, so so for example, you see, if you want to solve a span problem here, right? We can easily reduce the span problem into some augmented matrix calculation. Okay, similarly, if we're gonna do some linearly independent calculation, right? You also reduce it to augmented matrix. Okay, so that's why we like vector space. Okay, if you have a vector space, all these calculations will reduce to the chapter 1 calculation. Okay, augmented matrix. All the pivot story. Yeah. So as long as you have a vector space setting, then you can reduce your problem to augmented matrix. Okay. So I think later we'll see more. Okay, let's continue with our story here. So wait. So first theorem we'll see today is this spanning set theorem here. Okay, so what's the spanning set theorem here? So let's X be a set of vector, okay, and then hash is the subspace, okay, the subspace that's spanned by this V1 out of VP, meaning what? Inside this hash, right, is all the linear combination, okay, of these vectors. So there are two segments here. If one of the I think I cannot go too far today. I need to record. If one of the vectors in X, say Vk, is a linear combination of the remaining vectors, then the set formed from X by removing Vk still span H. Okay, so let me give you an example for A here. Okay, so let me give you an example. So let's say X is equals to the set containing 1, 0, 0, 1, and let's say 0, 2. Okay. God bless you. So say one of them is a linear combination of the other factor. So what does it mean here? So in this case, let's see that 0, 2 equals to 2 times 0, 1. Okay. And then the claim here is span of the first 3 vectors here is equals to the span of 1, 0 and 0, 1. Okay. Can you see why is it true? Or prove why is it true? Okay. So to prove this, for sure, you need to write down all the elements, right? So all the elements on the left-hand side looks like what? C1 times 1, 0 plus C2 times 0, 1 plus C3 times 0, 2. But on the right-hand side, you just have, let's say, D1 times 1, 0 plus D2 times 0, 1. So how do you like remove this 0, 2 to look like this? How? How? Any idea? Yeah, Edward. Yes, so you write it in terms of 0, 1. Then you can see that everything on the left-hand side also can written as a linear combination of the two vectors 1, 0 and 0, 1 only. Okay, so similarly, you can go from right to left, right? You can just use this to cook out an extra 0, 2. Okay, so you can go left and right, right and left. So they are equal. Okay, so this is the content of the first part here. And then part B says what? If H is non-zero, some subset of X is a basis for H. Okay, this is obviously true. This is obviously true. Okay. It just says that you can reduce the number of vector inside your X to be a basis. Why? Because this set of vector already span H, right? So what else you need to check? Linear independent. Okay, so the first part says what? If one of them is linearly dependent, you can just throw it away because you can create it anyway from the rest. Okay, so you just keep throwing. Okay, throw until you get a basis. Does that make sense? Okay, so for example, in this case here, in our case here, which one we should throw away? What do you think? Okay, we could throw away 0, 2. Okay, let's throw away 0, 2. If I throw away 0, 2, we can check that these two actually span and they are linearly independent. How to check linearly independent? You just form the basis and then check that there's pivot in every column. Okay. Actually, there's a second choice, right? Instead of throwing 0, 2, I also can throw 0, 1. Right, because I can always write 0, 1 as a half of 0, 2. Okay, I can throw the other one also. So there's a, how to say, there's a choice here. What doesn't change is the number of bases. Okay, this is what we call invariant. The number of this dimension won't change. Okay, who represent these two vectors might change. Okay, so again, sense space, you could have different bases. Okay, sense space could have different bases, but the dimension won't change. Okay, dimension won't change. Okay, this is a very important theorem actually. Later we will see again. Okay. Yeah. So this is about spanning set. Later we'll use it to show something on basis. Okay, so please remember this. As long as you have a, so what's the remark here? So you have a spanning set. Okay, you can throw away the linearly dependent guy until you become a basis. Okay, so this is the accent of this theorem. Okay, so before we talk about basis, basis theorem, it's a unique representation theorem again. The coordinate vector that we introduced last time. So we will do it for general vector space now. Okay, so first you should start with a basis. Okay, so meaning what? These guys are linearly independent and then span V. Okay, you can get V out of B1 until Bn using linear combination. Okay, then the content of this theorem is for every element in V, okay, we can write it uniquely. Okay, uniquely in this form, such that we can define it as a coordinate vector for this X. Remember last time we said that this coordinate vector is like an address. Okay, address for this vector inside this basis. Okay, if we change basis, the address will change. Okay, last time we do it right using R2 examples. Okay, so let's do it again in this example here. So consider, okay, is everyone okay or not? Before we move forward. So coordinate vector is the scalar, okay, scalar coming from this linear combination. We just read the scalar out and then it is unique. Why? Require proof. You need to prove it. Okay, we won't prove it. Okay, so let's check this examples here. So consider a basis B1, B2. So B1 is 1, 0, B2 is 1, 2. If X in R2 is such that the coordinate vector of X is negative 2, 3, find X. Okay, so what does this mean here? So this is actually checking whether you know the definition of coordinate basis or not. Okay, so this coordinate basis is the address for this vector living in the B basis here. Okay, so how to write it? It represents the scalar. Okay, scalar in front B1 and B2. So negative 2 times B1 plus 3 times B2. Okay. So if you want to see what's the general form here, so the general forms look like this. So if I write the coordinate vector as A1, A2 out to AN, then X will equals to A1, B1 plus A2, B2 plus A3, AN, BN. Okay, given that my beta is equals to B1 up to BN. Okay, so what you need to remember is coordinate vector is the address for this vector inside the basis B. Okay, so how to record the address? You need to know the coefficient. It is enough to know the coefficient, right? So you take the coefficient, you scale your basis vector, and then add them up. Okay, so in this case, what's the answer? Anyone computed? What's the answer? Sorry? 1 and 6. Okay, good. Okay, so the real vector is 1, 6. So in other words, what's the real vector here? So can we draw it? So in R2, where is 1, 6? 1 here, and then 6 here. Okay. Do you want to know what's the geometric meaning of this address? Can you imagine how to say it? Okay, so let's say maybe we go a little bit deeper. 1, 6 here. Okay, this is 1, 6, right? So if we look at the standard basis address, okay, standard basis address is very easy. You just take the first number as your first component, and then the second number as your second component here. Okay, so meaning you see our address is like this. So you have a 1 unit to the right, and then 6 unit going up. Okay, 6 unit going up. So let me draw it properly. So you have 6 unit going up. Okay, so well, okay, let me do it in scale. Okay, 1 unit going to the right, and then 6 unit going to the top. 1, 2, 3, 4, 5, 6. Okay, so your vector like this, look like this. Okay, but now you change the address. Why change the address? Because your basis changed. So what happened to your basis? Can you see where is your new basis looking like? Where is 1, 0? Okay, 1, 0 is still this vector here, but you are not looking at 0, 1 now. Instead, you are looking at 1, 2. Where's 1, 2? 1, 2 is around here. Okay. 1, 2 is around here. 1, 2 is around here. Okay. So you can see that your vector, so you can, okay, what you imagine is the y-axis you take, right, become this 1, 2 already. Does it make sense? Does it make sense? Okay, previously our basis is E1 and E2, right? So E1 is going this direction, and then E2 going this direction, right? Okay, but now your E2 become 1, 2. Planted already. Where's your vector? Your vector is on the left-hand side of this new basis here. So that's why you see your address here got a -2. Does it make sense? Because before that, if you are on the left-hand side on E2, right, you got negative in X. But now your E2 changed to 1, 2 already. And then your vector live on the left-hand side. So that's why your address got a negative there. Match out? Does it match up? Match out, right? Okay. Yeah. So this is what you are calculating actually. Okay. So it's the yeah. So the new address inside this coordinate here. Okay. Okay. So let's do B. Okay, let's do B. Find the coordinate of -2, 3 relative to B. Okay, so let's say we use this idea. Let's say we use this idea again. So -2, 3, where is it? It's already in the negative side. -2, 3. -2, 3. Yeah, okay, here. Okay, -2, 3. And then I have no solution here. Oh God. So you see that -2, 3 here. So it's also on the left-hand side of 1, 2. Okay, so you should expect that the coordinate also have negative. Okay, you should expect that. So let's compute it. Okay, so let's compute it. So let's compute this. Y. So we want to compute YB, right? Okay, so YB, how many terms? You need to know how many terms you try to compute first. What do you think? 2, right? Okay, because your basis only have 2. Okay, so you should need 2 coefficient here. Okay, let's call it B1, B2 here. Okay, what does this B1, B2 do? B1, sorry, oh, I use the same notation. Oh, it's very bad. So let's use C1. So C1 times B1 plus C2 times B2 should be equals to -2, 3. Or, okay, let it equal to Y first. Okay, and then we know B1, we know B2, we also know Y. So we solve this. Right. To solve this, what do? Again, you use augmented matrix. Okay, 1, 0, 1, 2, and then -2, 3. Okay, so you solve this. Hey, what do you get? Okay, maybe I quickly compute it. I should get -7/2 and 3/2. Okay, I think 3/2 is quite easy to see. You just get it. And then the other one, you need to add them up. Okay, yeah, so your coordinate vector is -7/2 and 3/2. That is. Okay. Yeah. Okay, so you can see that your coordinate basis is you have a negative x, right? Living on the left-hand side of 1, 2. Okay. Can see or not? Okay. Make sure you know what you are doing. All right. What time is it? 3, 4, 5, 7. Let's see what we're gonna do. Okay, before I take a break, maybe I tell you why this theorem is true. Okay. No need to copy anything. So I will roughly tell you why is this true. What's the idea here? Because this idea will involve what you have learned before. Okay. And then later we'll come back for a few more examples. So what's the idea here? So actually, secretly, you are seeing a linear transformation here. So what's the linear transformation here? is going from V to Rn. Where is going from V to Rn here? Why? Because this bracket thingy, right? You input a vector, output a n numbers. Scalar is n numbers, right? Okay. So actually it's a map going from a general vector space to Rn. Okay, so how do you prove this Ci is unique? What you need to do is you need to check that this map is 1-to-1, 1-to-1, and onto. Okay, but before that, you also should show that you should show that this is a linear transformation. Okay, yeah. So for example, linear transformation means what? And some of you say, a lot of you say you haven't mastered linear transformation yet, right? Before taking the quiz. But hopefully you will, because will we see again? Seems like we won't see again. So it's just chapter 1. Okay, so you need to revise for your final. What is linear transformation? Basically, it's just a function. Okay, a function that do two things. One is preserving addition. The other is preserving scalar multiplication. Okay, preserve means what? So if you put, let's say, put x plus y inside this map, right? It is equivalent to doing this map on the individual element first and then add them up. Okay, so this is the first step. Second step, if you apply this map on a scalar multiple, it is equivalent to doing the map on the individual first, then scale it. That's all. Linear transformation, that's all. Okay, it's a function that satisfies these two properties. Okay, you can pull the scalar out or you can split the sum. That's all. Okay, and then you need to check that it is 1-to-1 and onto. Okay, why onto? You need for every x, you need to find such coefficient. Why 1-to-1? This set of coefficient must be unique. There's only one solution to solve it. Does it make sense? Okay, so the idea of this proof involves whatever we learned. Okay, involve the linear, the 1-to-1 and onto linear transformation we learned before. Okay, I will put out the proof for this theorem, but we won't test it. Okay, but the idea is what we learned before. Okay, any question? Okay, so one thing to observe here, what's the dimension of Rn? What's the dimension of Rn? Huh? What's the dimension of Rn? Sorry? What's the dimension of Rn? N, right? Okay. You also know that how many vector inside this V? Also N. Okay. So we are actually building bridge between n-dimensional vector space and Rn. Okay. Okay. Remember last time we gave you different vector space, right? Space of polynomial, space of function. That doesn't look like Rn, no? Correct or not? They are function, they are polynomial, not vector. Okay, but there's a bridge from all these vector space to some Rn. Depend on the basis you have, the number of bases you have. Okay, so if you have M here, Bm, then you have a map to Rm, like that. Okay, and then what's the map there? You just read the scalar. Just read the scalar. Okay, scalar in front of these bases is important. Okay, that's why we can apply matrix calculation to vector space. Okay. Okay, so if no question, let's break until 4:12, and then we'll come back for some more examples. A
这个 Rn 的 dimension 是 n，
啊哈，
说这个 Rn 的 dimension 是 n，dimension 不是它那个个数，
对，没有错，不是 vector 的个数，是 basis vector 的个数。
嗯哼，
啊哈啊哈，
是 Rn 不是一个这样的数吗？
对，没有错，对，
有 n
所以我的对，没有错，所以我的 claim 是说有 n 个 linearly independent 和 span 是个 space 的 vector。你可以
也可以把它这样反过来看，反成一个这样的东西，就是这个 Rn。
啊哈，没有 Rn 对 Rn 里面的东西是长这样的，这样嘛，对不对？所以我的意思是说，它是 span of n 个 linearly independent 东西。你还记得谁会 span？诶，可以演，不能
出去。
哦。所以有 n 个东西是 linearly independent，而且可以 span。就是我们每次说的，就是 standard basis。你只要选 standard basis 就行。的 stand 的是那个1、1、1、2、1、3。对，对，你知道为什么他们 linearly independent 吗？然后它 span，为什么它 span？它 span 的理由很简单吧？
就吹呗。
因为你只要拿 S1乘这个 S2乘这个 S3乘这个 S，加起来就是所有的，可以得到所有的vector。那个 n 是在指这个有 n 的 basis 有 n 的。
哦，
对，
那就
它里面东西肯定是无限的，因为其中一项已经无限了。为什么 n 是因为它的 base linearly independent 跟 span。
还有一个问题是，之前
你先看，
他先帮我找，
你先 OK。
这个我不知道
怎么乘出来？
对，
你就如果你要的话，你可以把这条线丢掉，其实，但是就正常乘吧，因为这个是3乘3嘛，这个3乘4嘛，所以它乘出来的 matrix 是3乘4。对，就这样。
就一个一个的乘。
就一个一个乘。I mean，你要检查的话，你这个乘这个可以得到这个，这个再乘这个又得到这个。这么多了一个哦，因为这里有2步，所以这2个乘出来会是这一个，然后这个乘这个就是这个。
如果就乘最后一行的话，就是8，然后就是要算这个算14这个，
对，
然后这个
对，
就是然后减262，然后加0再加8。
没有啊，你每一个一个都要做出来，一步一步做啊，怎么是可以跳过来的？一步一步啊，它是一步一步的。
就乘最
对，
后
你要一步一步啊，你要这个做出来先，它第3列就开始变，第4列就开始变了，这一步它已经变了，这一步再变，再变，呢，变，
好的，
不能够直接这个走在这个上，那个是另外一回事嘛，你自己想一下，如果我把这个做在这个上面，是不是长不一样的东西？
这一列，就算这一列的话，不就是这一列，然后乘这个。对，
但是你不能直接跳过来这边做啊，你是跳过来这边做吗？你要连着做。
就是这个乘这个
先做这一个嘛，对不对？
先这个乘这个加这个乘，那就
喂，没，哦对，这一个乘这一个会得到这一个，这一个乘这一个会得到这个，这一个乘这个会得到这个，然后在这一个再乘这新的。对，你不能够这个单做这个，这个单做这个，不可以，因为它会变啊，这2个还会变啊，会跟着这个变，你明白吗？你想想看呢，你拿这个乘着这个就开始变了啊。 对不对？这个是3乘3嘛，3乘1嘛，你不能够看这一个就单单看这一个吧，因为你要想看下一个是要对所有的3个一起作用，所以你后面会有变的话会影响的。对对。
还有就是周5考的 quiz 就考第2章。
对，没错。
对。然后问一下，像这个我们找它的这个 basis for common space 之后，我们这样通过找它的这个东西，对 capital 的 common 找完之后，我们还要再重新证明一下它的 independence。不用，因为它就已经默认了它已经是 independent。对，没有错，那是 theorem。对。那就是化简之后直接写 yes。yes。对，没有错。
我刚才讲修到几点？我刚才讲到几？12哈，好吧。想打球哦，教到6点哦。没有错。什么叫难怪？难怪这样监控啊。比较闲控啊，比较闲控。杜家伟，谁是杜家伟？老铁，是家伟嘛？哦，你是董宏伟。哦，你是董宏伟。OK。李亚航、李延轩、翁佳命、郭书涵、OK。蒋生杰、涂天天、OK。你上周一有在吗？你不在，OK，你不来。去新加坡玩，这么开心，下次可以带我。玩越好。严子轩、高峰、唐丹、年幼、董宏伟，你周一有在吗？你去哪里？什么？有点事情。OK。郭明哲、何军 ，OK。依林，啊，依林还是依林？依林。新宇有在 ，Bryson here right？OK。黑后训，郑瑶在，方林 ，OK。秋子，多少啊？退了。云溪 ，OK。子珍 ，OK。林星宇呢 ？OK。心仪在哦 ，OK。Nicole Tong，刷玉界，曹子瑜，胡生宇，OK。Okay, so time's up. So let's continue discuss. Okay, let's do one example on Rn and then one example for polynomial. And then the other one we left for homework. Okay, so let's do this. So show that B is a basis of R3. Basis means what? Basis. Two keyword. Span and linearly independent. Okay. So how to check? Hey. Oh, not yet. I haven't finished taking yet. No worries. I'll continue later. Okay. Right. Okay. So one way to do is what? One way to do. Okay, should I teach you method? Teach you method. First, if you want to ask why, then we can discuss. Okay, so method 1. Okay, you can show from definition. Okay, so definition says what? Let's say for span. So this one, what's the subspace here? What's the space here? R3. Okay, so for every x in R3, you need to show that there exists C1, C2, C3 in R such that C1, V1 plus C2, V2 plus C3, V3 equals what? Equal X. Good. Okay. So meaning if you write out all the given vectors here, no need to copy first. You can listen first. I will provide notes on. Unless I ask you to calculate. Okay, so meaning you want to solve this. To solve this, what does it mean? You need to solve the augmented matrix. Does this look like your quiz question? Right. Okay, so you want to solve this and then you ask whether this is always consistent or not. Okay, you always have solution or not. Okay. So I want to say that check if the associated augmented, associated linear system is always consistent. Okay, so if it is always consistent, then their span R3. Okay. Okay, so this is a very original method. So what I want to you is reduce yourself. Okay. How about second one? How to check linearly independent? Actually, the question is asking around the same vector equation, right? But in this case here, instead of random x, what's the specific x you need to look at? 0, very good. So when it is equal to 0, if and only if the 0 solution is the only solution. Okay, meaning what? You need to check that if I substitute x1, x2, x3 equals 0, there are pivot in every column. Okay. So we should expect what? This augmented matrix here as pivot in every column. Okay. Is anyone not happy about this? 有人不理解吗？为什么解一个零的答案跟 pivot 有关系？有什么人不理解吗？在这个班上，不理解不用紧，你 final 的时候要理解。现在不理解不用紧，有人不理解吗？不理解 ？If you don't understand, I can explain again. Anyone doesn't understand? Why solving zero solution is equivalent to pivot? 如果理解的话，我就抓一个人来问了哦。谁？好像有一个叫天天的，天天在哪里？Who is 图天天？Hi 天天 新加坡好玩吗？没有。Okay. So, 天天 so why to solve zero is the only solution is equivalent to fact that it has pivot in every column. Why? Okay, I give you some hint. If you have a pivot in every column means what? In this case here, sorry. You will see this kind of form, right? Okay, so then. So how to explain this solution here? Oh. 不懂 OK， 谁懂谁是他朋友可以救一下他们。你有朋友吗？在这个班？你没有？这么可怜？找一下你同辈的人，有好多 ACC 202409，超分就不要了，找另外一个没有讲话的。颜子轩在那里，会颜子轩。Okay, so why if you have pivot in every column implies that your solution is only 0? Why? 大声一点，大声一点，越来越小声。答案是 fixed， 怎么看？怎么看答案 ？How to look for the answer? You don't know how to say? So if you look at this, what you can deduce? What can you deduce from here? Sorry? I mean, if you look at this REF, right? How you write down the solution? What's the general solution? And then C3 is 0. Actually, how you read these, supposingly you should write C1 plus 0 plus 0 equals to 0, right? And then 0 plus C2 plus 0 equals 0. And then 0 plus 0 plus C3 equals to 0. Okay, so you actually see this one as the coefficient for C1, C2, and C3. Does it make sense? Okay, so this is what I test you in quiz question 2, quiz 1, actually. How to go from a augmented matrix form to a linear system. Okay, this is what I test you on question 2. Later we'll discuss. Okay, yeah. So you need to make sure you know how to go from this augmented matrix to linear system, and then go from linear system back to augmented matrix. Okay, come back and forth. Okay, so this is why we say C1 is 0, C2 is 0, C3 is 0. Because we successfully make other variable into 0. Okay. Okay, so this is a very traditional method, right? Method 1 and method 2. So if you notice, both calculation involve what? Involve solving augmented matrix. So what you really need to do here, let's use method 2, quicker. So let's use method 2. So instead, once you see this kind of question, right, you can write down the matrix first. Okay, so you can write down the matrix formed by, so form the matrix using the V1, V2, V3. So let's say form M to be a V1, V2, V3. Okay. So if okay, so let's write down. So let's do this properly. So so then in this case 1, -2, 3, 0, 2, -1, 3, -1. Okay. So form this matrix here, and then we row reduce it. So let's row reduce this. Can we quickly do that? Sure, let's do this. So 103. Zero 27, 0 minus 1 minus 110. Okay, so what do I do here? Row 2 plus 2 row 1, row 3 minus 3 row 1. Okay, it's not REF yet, right? So let's continue. Continue. What do you get? What do I want to do here? So there's two choice here. Okay, two choice for your next pivot. Yes, I think I will save -1. So I kill 2 first. Okay, so let's kill the 2 first. And I notice some of you still cannot do row reduction. A bit pity. You need to ask me how to do it if you cannot follow. Okay, and then I move my pivot up. Okay, and then what to do here? So I scale my leading entry, all the leading entry to be 1. So can put -1. Okay. And then I think now pretty good already, right? It's pretty good. So what can you see here? 1, 2, 3. Okay, so you see that every row has a pivot. Okay. So meaning what? The associated linear system is always consistent. Okay. So uh so the set will span R3. Okay. So why? So why? You don't need to write in your exam, but why is it true? So you should imagine if I'm gonna solve any B1, B2, B3, right? Okay. You can always find a solution. Okay? Yeah. Why you can always find solution? This is also one point you guys miss in quiz. Because you won't have the case 0 equals something non-zero. But some of you says 1 doesn't equal 0. So the system is inconsistent. That's false, Because you know what this 1 represent or not? This is 1 time C3. It's C3, not 1. No. This 1 is not 1. Okay. Does it make sense? Okay, later we'll discuss with you. Okay, so this is one clean way you can show span. Okay, the other method for linearly independent is similar. So it's the same, right? Look at this, the same REF, but in the second part, you should say that every column has a pivot. So the associated linear system has a unique solution. So what's the associated linear system that you're interested in? Actually, it's a homogeneous. Has a unique solution. Okay. Homogeneous is when all the B1, B2, B3 are 0. We call it homogeneous. Okay. Yeah. Has unique zero, has a unique solution. Hence, beta is linearly independent. Okay. Yeah, so instead of solving from the definition, right? You see there's a long way to go, but in the end, you still solve for the row reduction of your matrix. Row reduction echelon form. Row reduced echelon form. Okay. Yeah, so you just go into calculate your matrix, REF of your matrix is enough. And then you check if you have enough pivot or not. Okay. Yeah. Actually, there's a third method. Since you learn determinant before, right? So you can use determinant to check also. Well, we can use determinant to check. Okay, so let's compute determinant first, and then I'll tell you what's the story. So if we compute determinant of this matrix here, 103. Okay, 3 and what? -1, -1. Okay, so Xingyu, can you try and help us compute this quickly? Since you spend so many time learning this. Can you quickly compute what's this determinant here? What way you're gonna use? There are a few ways we learn, right? We use core factor expansion or elementary row operation. Okay, which one is faster? Core factor. Or let's try core factor first. Which row you want to expand? Or which column? Okay, first row. So what do you write? 1 times the determinant of the first minor. Then what's the next term? What's the next term? So you take row 1 first column, right? Oh, I take the row minor, is it? So this minor should be -1. First row, first column. And then first row, second column. Okay, but the scalar term is 0. So we don't care. And then first row, third column, we have 3 times -2, 1, 3, -1. Okay. But remember on your signature, so the signature here is plus, minus, plus. Okay, so plus, minus, plus. Okay, so in the end, what do you get? Anyone computed? -13, good. Okay, so this is non-zero. So determine non-zero means what? Remember the theorem. If the determinant is non-zero, meaning what? Matrix is invertible. Good. So matrix is invertible, also equivalent to what? It is row equivalent to the identity, because you can row reduce to find your inverse, right? Row equivalent to identity. But row equivalent to identity means what? The RREF of this matrix has pivot in every row and every column. We settle everything in once. Okay, so this says that the RREF of M has pivot in every row and column. Okay, so B span R3 and is linearly independent. Okay. Okay, no. Okay. So like last time I told you, right, there are a lot of equivalent statements for invertible matrix theorem. So instead of checking determinant, you can check all the other condition. and you can check all the other conditions. They're equivalent. Then once you get that this matrix is invertible, then it is row equivalent to identity, then it will have pivot in every row and column. Okay. Yeah. So yeah, using any way to check is fine. Just find the quickest way. Okay. Any questions so far? So far, any questions? No? Clear? Okay. Okay. Right. How about next question? Find the coordinate of x 17 minus 1, 2 with respect to b. So what does this mean? Maybe I ask you first, see if you know. What does this mean? So I want to find the bracket x in terms of beta. So this is a vector. How many numbers inside this vector? Who says something? 3, right? Because inside this b have 3 things. The n is 3. Okay, so there are 3 things here. But what does this 3 number do? So what's the definition of this coordinate vector? What does this C1, C2, C3 do? Satisfy what equation? C1 times V1 plus C2 times V2 plus C3 times V3 equals to X. Okay, so again, solve the linear system. Okay, so we skip this. Okay, let's skip this. Okay, let's go to a different vector space and then see how we show basis. Basically, in this class, I guess the most important vector space is either Rn or this one. Okay, we do a lot of example on space of polynomial. Okay, so these two you should be familiar. Others is fine. Okay, so how to check? This is a basis. Oh, this one a bit tricky. There's no vector. How to check? There's no vector. How to check it? So what do you do? Go back to the first principle. Okay, go back to the first principle. So let's use the method 1 again. Okay, use the method 1, the first principle. Is it true that for every a plus bt plus ct squared in P2, I can express it in terms of, use what notation? PQR. Yeah. MN or LMN, DEF, GH. No more symbol to use. Let me think. XYZ? XYZ. Okay, use XYZ. So, I mean, use P got already, P got already, C got, E got. What to use? P. X. Okay. So X1 times P1P plus H2 P2 plus H3 P3 is equals to A plus BT plus CT. So does that exist? H1, H2, H3, such that this is true. Okay, so this is for span. So let's write it down for span. Okay, so if you expand everything, right? What happens if you expand everything? Very long, if you expand everything. So H1 times 1 minus 2 squared. H2 times. And then plus H3 times 3. Okay, equals to So what do you do next? You expand everything out, and then you compare coefficient. Okay, you compare the coefficient for the degree 0 term, and then degree 1 term, and then degree 2 term. Okay, so can we quickly do that? Anyone know what A equals to, B equals to, and C equals to? Can quickly compute this. Try compute, see if you do the same thing. What do you get from the 0 degree 0 term? H1 plus 3H3, good. H1 plus 3H3, and then B equals to? Okay. Good. Just H3. Okay. Next. 3H1. H2. And H3. Okay. So you want to solve for H1, H2, H3, right? Linear system. Again, you make it into augmented matrix. Okay, so you solve this. So what's the question asking? Show that B is a basis. I think this type of question already is a bonus question. What does it mean? Bonus means what? I already tell you it must span. It must be linearly independent. So your calculation should get pivot in every row. Okay. If you don't get pivot in every row, there are two cases. Okay. Either your calculation is wrong, either the question is wrong. Okay. Yeah. Okay. So if you think that your calculation is right, the question should be wrong. Okay. So I think I don't want to do this in class. So you can go back and check. You should get this REF. Okay. So we really get pivot in every row. Okay. Also, you can see that if I substitute A equals 0, B equals 0, C0 equals 0, this also explains the linear independent. Okay, because have pivot. Pivot in every column. So in this case, so since there are pivot in every row, okay, so span R3. Hey, sorry, span what? What's your vector space? P2. Okay. And then second part, from the above REF, beta, right? Beta is linearly independent because there are pivot in every column. Okay. Yeah. So you see, can you notice something? Actually, how we get this? Can we directly get this? Is there a direct way to get this matrix? By looking at this three polynomial here. Can you reckon? Okay, yeah. So do you have a direct way, like? So let me move them closer. Copy. Paste here. So the problem is just to check the REF of this particular matrix, right? Okay. But my question now is, can you directly see the matrix from this three polynomial? No? Can you directly see it? Huh? What? 打直. What do you mean by 打直? What do you mean by make it vertical? You mean like this, vertical like this, not too far away from the solution, not too far away. Actually, what do you notice here? What do you notice here? Just now you see something like this, right? Something bracket of some beta, right? Okay, so they use beta here, so let's not use beta, use C here. You will get this vertical thing. But now the vertical thing that you want to get is 1, -2, and 3, right? So what's the C you need to pick here, actually? What's the C that you need to pick here such that you get this vertical thing? Still remember what does this coordinate vector do or not? These numbers should be a coefficient of some basis vector. So who are the basis vector here? Huh? 1, t, and t squared. Yeah, or not? So if you pick this as your basis, right, then you will get this matrix out. Okay, and then you just check whether this matrix has pivot or not in every row and column. Okay, yeah. Why it works, huh? Why it works, Why it works, huh? Okay, because of the theorem that we proved just now, the unique representation theorem here. Okay, once we have this one-to-one and onto maps, right? Okay, we said that these two space actually is isomorphic. There's a bijection. If did you guys learn bijection before? I think SWE DMT should learn bijection before. Huh? Correct or not? So bijection means what? One-to-one and onto. Okay, one-to-one and onto means what? I can hit everyone in the core domain. Okay, but everyone in the core domain has only one pre-image. So meaning what? If I have 4 elements inside V, I also have 4 elements inside Rn. Somehow I can recover one from the other. I can go from one space to the other space without losing information. So there's a bijection. Okay. Okay. Yeah. Yeah. Okay. So if you don't understand this part of theory, to be safe, you just go back to method 1. Use this method 1. Okay, go back to definition. If you know what am I talking about, you can use this method here. Okay, cook out this matrix using a nicer basis. Okay, cook out the matrix using a nicer matrix. Okay. If you know, you can use this method too. If you don't know, no need to use. Just go back to method 1. Okay, because I don't want you to use method 2 without knowing what it's doing. Okay, yeah. Okay, if you understand what I said just now, you can use a different basis, then it's fine, you can do it. Otherwise, just go back to your original method. This method will work for any case 1. Okay? Okay. Okay. Right. What time is it? 4:48. Let's see how many more to go. Okay, maybe we'll talk about dimension and then we will take a break. Okay, so this one left as homework. Okay, this one. So we'll introduce the idea of dimension. So dimension of a vector space. So the theorem is if a vector space has a basis B1 up to Bn, then any set in V that contains more than n vector must be linearly dependent. This is what we discussed before, right? So if you have more, so last time, okay, so let's recall what's the theorem that we say last time. So last time, we said that if p greater than n, then what? V1, V2 out to VP is linearly dependent? Dependent, right? Okay, but where's the n come from? Where's the n come from? Sorry? Sorry? Span? What do you mean by span? Span of what? Oh, this. Okay, so this Vi, right, supposed to be an element in Rn. Okay, yeah. Okay, so this is where the n come from. Okay. So actually, this theorem is a part of this big theorem here. Okay, if the vector space has a basis B1 up to Bn, why? Because in Rn, what's the basis here? This is the span of the standard basis E1, E2 up to En. Okay. But if you have more than n vector, it must be linearly dependent to the rest. Okay, this is what you use in your quiz also, right? If this number of vector is greater than this dimension of Rn. Okay. Okay. Is it okay? Need example or not? Need example? So example, if you want to see, is something like this. So let's say, so let's look at this one. Okay, one of them must be a linear independent of the other. Okay, because in R2, the basis is what? You can pick E1 and E2. Okay, E1, E2 is already inside here. E1, E2. And then all the other vector must be a linear combination of these two. Okay. Note that, there's one thing I want you to note here. If you can write 2, 1 in terms of 1, 0 and 0, 1, right? You also can write E1 in terms of the other two, or E2 in terms of the other two. Correct or not? You just swap inside your equation. Okay, so if you don't understand what I mean by swap, right? Let me quickly write to you. So you can see that 2, 1 is equals to 2E1 plus 2E2. Sorry, 1E2. Then you can write E1 as what? 2, 1 minus E2 divided by half. Or you can write E2 equals to 2, 1 minus 2E1. Okay. You can throw any one of them away. Okay. So far, okay? Okay. Okay. Next, if a vector space have a basis of n vector, then every basis of V must consist exactly n vector. You know what this sentence trying to say? If you know that the vector space have basis of n vectors, if you choose another basis, another set of linearly independent and span, it must also consist exactly n. Cannot be less than n, cannot be greater than n. Okay, if it is greater than n, you can throw it away. Okay, if less than n, it won't span your vector space. Okay, so this is the idea. Okay, but to prove it, I think we need to use a previous theorem. Okay, yeah. So this will pretty much decide the definition of the dimension. So the dimension of vector space will make sense. Okay, because it won't change one. No matter what vector you pick, okay, if you pick a different n vector, this number n cannot change. Okay, so for a vector space, the dimension won't change one. Okay, although you can change the choice of basis. Okay, yeah. So this number is very important. This is what we call a invariant of a vector space. So invariant means something that doesn't change. Okay, I give you a vector space. This number cannot change. It won't change. Right? Okay, it's specific for a vector space. So we will say that if V is spanned by a finite set, then we will say that V is finite dimensional. Okay. And the dimension of a zero space is always 0. And if, let's say, the base set of bases inside the basis set has infinite set, we will say that V is infinite dimensional. Okay, so they are finite dimensional and infinite dimensional. And to answer what Southern asked last time, right? If V is spanned by a set with n elements, then V is set to be n dimensional. Okay, so for example, if you read news or science article, they'll say that, oh, we are living in a 3-dimensional space. Or if you include time, we are living in a 4-dimensional space. Like that. Yeah. Okay, if you read some news on science, how many dimensions? So after you learn linear algebra, right? So you should know that this dimension refer to linearly independent and the spanning set. Okay, there are n elements there. Okay. Okay. Okay, so before we end, I want to before we go to the next part for the next hour, I want to throw to you one very new concept here. So this is a very frontier research, which is what we do. I do actually. So basically we start with a V, right? Just now, okay, vector space. And then we find a set of bases. The end. And then we have this construction called the dimension. We take the number out, call it n. Okay. And then this n should be what? Can be negative or not? Can you count negatively? Cannot. Right. So it's a positive number or say natural number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So this is a construction. So for example, let me show you amount of things that we know. For example, R2, R3, Rn. So what are the dimension? R2, the dimension is 2. R3 dimension is 3. And then Rn is n. For example, another one, P2, just now we show. Degree, polynomial of degree at least, at most 2. This is 3. Okay, so in general, Pn will go to n plus 1. Okay, plus 1, why plus 1? You need to consider your constant degree term. Okay, that's the plus 1, where it get from. Okay, and maybe we didn't prove, but I'll let you know that, for example, R infinity that we showed last time, the infinite series sequence, sorry. This dimension is infinite. Okay, you should imagine that what's the basis here? The basis here should be the standard basis also. But you imagine that this standard basis never end one. End. Because there are infinite term here. Okay, so the standard basis never end. And then another example we learn, right? Set of real value function. Okay, this guy also what? Also infinity. Okay, so you can see that on one world, we have this basis. Sorry. In one world, we have this vector space. In the other world, we have natural number. is more natural? What do you think? Which one is more natural? Which one come to you first? Sorry. Left hand side or right hand side? You think it's more natural to you? You think this is more natural, right? 谁讲的？高分哈。You think this is more natural? Okay, let me tell a story. How max advance? So let me tell you a story. When do we start counting? What do you think? Okay, if we say from a point of view from this shepherd, you know shepherd or not? Shepherd. Yeah, shepherd who raised the sheep, right? So they raise sheep. So how to draw the sheep? Okay. Okay, I told it from the viewpoint from maybe Middle East there, they raise sheep, right? Maybe in Asian we raise chicken. Correct or not? Okay, so here is a shepherd A and a shepherd B. Two shepherd here. So shepherd A raise some sheep. So let's draw a circle here, lazy a bit. About shepherd B, also got some sheep. I need to copy, this one not in test. I want to give you an idea. Okay, so they raise a sheep, a herd of sheep. So one thing is, we want to compare. They want to compare who got more sheep. How to compare? You got one, I got one, right? You got one, I got one. You got one, I got one. I got one, you got no more already. So I know that A has more sheep than B. But what's the other way that you can compare? I can count that I have 6 sheep for A and only 3 sheep for B. Also, I can see that 6 is greater than 3. And this number is an invariant of the sheep, of the number of sheep, of the set of sheep. Hey, how to spell sheep? SHEEP, right? Okay, so this is the invariant. Okay, no matter how your ships run, okay, no matter how your ships run. So let me see. So let's say this is number 1, number 2, number 3, number 4, number 5, number 6, right? No matter how they run inside here, or still 6 of them. Correct or not? For example, in your class, right, there's 90 of them. If I shuffle around, it's still 90. This number won't change one. So it's the invariant, okay, and of this ships here. So you see, which one is more natural? Actually, ships is more natural, right? How you learn number actually? Who teach you number? Your father or mother? Who? Often who teach you number? Who give you the idea of number? Your teacher, eh? So you already know it after your kindergarten, not at home. Maybe yes. Hey, you should think about it. Who is the first person who teach you number? And how that person teach you number? I don't know. Maybe, Apple, yes, good, exactly. The first person who teach you maths, that should show you some object that you can see. Either 1 finger, 2 finger, 3 finger like that. Like 1, like that. You understand or not? 1 apple, 2 apple, 3 apple. So the first time you learn number actually is through object. Only then you abstract to 1 plus 2 is 3, 3 plus 2 is 5. You understand or not? Okay, so in other words, actually these objects, this vector space, Actually, it's more natural. Actually, more natural. And then another thing is you can attach different things to 2. For example, 2 apples, 2 banana, 2 finger, 2 person, 2 classmates. Different object can be attached to the same number. Okay, and then this idea is very great. Attaching different vector space to the same number. This is what we call categorification. Okay, this is a very deep research area we are doing now. Maybe in future, your son need to learn it, or your children. Okay, yeah. Okay, so yeah, if you're interested, then you can work on this. Because in future, if you work into AIs, language of AI, I don't know DMT, SWE got do it or not. Maybe accounts need to use AI in future also. So this AI is using this language. Yeah. Okay or not? Yeah. Okay, so let's take a break until 5:15.
这个 null space 的这个概念到底是什么？
哦，OK，
我知道它定义是 a 乘 x 等于0，
没错。
但是我怎么用这种就是 matrix 里面去找它这个 null space
？OK， 好，非常好。所以你先把这个 ax 等于0 set out 起来先。说 ax 等于0是这么写嘛？
对。
然后你的 a 是谁？你要看这个人的。
就比如说这个吧，对，然后这个是它那个 reduce 的。
好，非常好。OK，你非常好，非常好，你 reduce 出来了 ，good。And then 你找它 general solution，good， 非常好。
Basis for null space。
没有错，没有错。所以你
它这个是一个东西吗 ？Basis for null space 跟 null space 不是一个东西。
不是 ，basis 是 for 一个 subspace， 所以 null space 是一个 subspace， 对啊。
是 basis subspace。
No。wait。等下，你讲什么？再讲一次。
我说 null space 是 A 的一个 subspace。
错。null space of A 是谁的 sub？ 是谁的 sub？ 是谁的 ？OK， 写这边是谁的 subset 啊？你要看，因为它是从哪里来？它是从 R5来，你写对了。所以意思说它是 R5的 subspace。A 没有 subspace，A 是一个 matrix 罢了，它不是一个 vector space， 所以你不能讲 space。它只是单一个东西 matrix， 你懂什么意思吗？
等一下，我现在等一下，这个 R5这个老师是您上课时候写的，
是我写的，不是
这个是您写的，对。然后我看这个我就有点不明白，它这个 R 几不是看它数字有几个数字？
没有错，数字有几个，但是要怎么看数字？有2个数字嘛，一个是3，一个是5嘛，你要选哪一个？对不对？你要选哪一个？现在的重点是你 A 要乘上这个 x 过后才是0，所以你要乘5，你这个 matrix 要怎么乘？3乘5应该要乘谁？对，
乘一个数个的是5个的乘的。
没有错，一定是5乘1哦，不可能3乘1乘不起来。对，没有错，所以这个东西一定要活在 R5里面哦。对，没有错。然后所以你只是在 R5里面去抽所有能够让这个 A 等于0的一个 factor， 对不对？然后你就把答案写出来咯，然后你就说 now A 等于 span of 这个咯，就对了哦。OK， 下一个东西是这个只是 span 嘛，对不对 ？Basis 还要符合另外一个条件嘛 ，linearly independent。所以你现在要检查说这3个是不是 linearly independent？ 怎么检查呢？你又要去 set out 那个什么 C1 乘这个 C2， 比如说这个叫 V1， 这个叫 V1， 这个叫 V3，C V1 加 C2 V2 加 C3 V3 等于0哦，然后你再去解那个 REF 哦，但是你解来解去就是把它变成 matrix 嘛，然后就直接 REF， 听得懂不？有点快。
就是不是，我还是等一下，我还停留在这里。
OK，
就是我这个，然后可以写成一个这样子的形式，然后因为他们这样子，我解出来一个这个，所以他们本来就是 linear independent， 所以它应该是一个。
No， 没有这个意思，没有这个意思，其实要证明了 linear independent。
要证明。
对，你看这个只是 span， 因为它是 coefficient 乘 vector，coefficient 乘 vector，coefficient 乘 vector， 然后加在一起，这个不是就是 linear combination 吗？这个就是 span 的定义。
可是那这个是 basis， 我这个得出来的话，我证明它是 linear independent 的话，它就应该是 basis for 这个 null space。
没有错。
但这个 null space 它自己是谁呢？我不知道。
是谁？就是说，你看啊，
乘一个 x， 然后乘完之后这个会等于0，然后 x 是谁？就是它 null space。
对，就是 OK。 这个 S2 S3 S4 S5的概念是什么？就是你可以任意选。OK， 任意选，假设啦，我选001。等这个东西如果放回这里的话，就是说 A 乘这个东西肯定是0，A 乘这个东西也是0，A 乘这个东西也是0，A 乘所有的组合都是0，所以这个就是它的 null space。所有可以让 A 乘起来等于0的 vector 就是我在 null space。就是这句话，就是这句话。
还有一个这个就是有没有 A 它没有 basis 的没有，你就比如它这个 row reduction 就是这个 A 吧，比如说我找这个
OK， 等一下先 ，before that，这个问题是 basis of 谁
of A 吧，你比如这个
没有 ，basis 是 for subspace。还记得我刚才画的那个关系吗 ？vector space subspace 才到 basis， 一定是 subspace， 不是一个 matrix 的 matrix 不会有 basis。
不是 A， 如果我说它是一个 vector 的话，然后就是它 column 这样子的话，它不是也本身可能是某个东西的 subspace？
没有，你那个要讨论的是 column space of
A。column space of A。
不是 A 本身。对，没有错。
那我就比如说，你说这个 column A 的 subspace 有没有可能没有 basis？ 你看，如果说我说这个 column A 的 subspace 的话，就是肯定应该也是写成一个这样子的形式吧。如果我去找它的 basis， 然后我 row reduction 之后，您不是说它 row 上面也有pivot， 然后竖的那个 column 里面有 pivot 嘛？然后你看这有一行它都没有 pivot 的话，那不就证明的话它没有办法span 了吗？
你现在是要看 column 还是看 row？ 不同的看法。
就是我是找 basis 不两边都要看吗
？No。
刚刚讲的不是跟这个不是
No， 我们解两个问题。我们那时候解两个问题，你要注意啊 ，basis 要配 basis 要配 subspace。一个是 for col A， 一个是 for row A， 有差别。同时，它不同的 subspace 是不同的。
我看看这个不是我说的是这里，就是这里。
我一开课的那个东西。
不是这个东西，这里就是比如说我们找这个的时候。找 basis of 一个地方的时候，对吧？我们要证明它是，我们要证明它是，首先要找它，首先要有 pivot in every row， 所以它 span 这个东西，然后接着说它每一个 column 里面都有 pivot， 然后证明它 linear independent。
对，没有错。
那 basis 不就是首先它要 span， 然后同时它要 linear independent， 它本身
你冷静。
我没有不冷静。
因为这个 basis 是 for 这个 P2 的。对，你不能够所有说找 basis 都是用这个方法，它要属于的 basis， 属于的 basis 很重要，属于的 basis， 你明白吗？属于的 basis 很重要
那就比如说这个吧，这个东西，如果我 row reduce 完了之后它是这样子的，比如说然后-2，然后1，然后3，-1，-1，然后我多一行000的话，那是不是就说明贝塔这个东西它不是 basis of P2？
没有错。没有错，你知道为什么吗？
因为它多了一个 row， 所以它就不是 span P2， 所以它就不是 basis。
No， 不对，它的原因是 linearly independent。因为你看，如果你做 row reduction 呢，它还是有 pivot in every column 的，就是说你可以解的。
对，
你可以解。我想一下
就是不 span， 因为如果后面还有一个的话，
你这个很夸张，不可以乱乱加这一行我觉得。因为你知道为什么吗？因为你知道这3行是从哪里来的吗？这3行是从 T 跟 T square 来的。
对。
你加做这一行什么意思？你要进到 T cube 进去了
那
不可能。
换这个。
OK， 好，换这个。
就是我再加一个 vector 4吗
？OK， 这个可以。
给它加一个 vector 4的话，不是，
所以你加
你是多没有 vector 1再多一个东西 ，vector 2再多一个东西 ，vector 3再多一个。
这个就去不同的世界了，不是 R3 了，
那就是
多一个，那是 R4 了。我觉得你要加的是加横的加，对，我觉得你要加这个。如果你加下面的话是不可能的。
那如果我在 R4 里面呢，然后 X。我在 R4 里面，然后找这个 basis，但是我 row reduce 完了之后，发现 R4 的 row reduce 的这个 matrix 的最后一行都是0的话
，OK， 想想看，但是有几个数量很重要，你要4个还是？
那如果只有3个呢
？OK， 非常好。
就是如果它不等呢，就是我的 vector 的数量和我的。
对，不等有几个条件嘛，一个小过，一个大过嘛。
对。
你要小过啊，现在。可以给我想一下。 你要小过，然后你下面又要零，
零，对，
就现在。OK，两个问题解决嘛，一个是 span，另外一个是 linearly independent，你要讨论哪一个
讨论
？linearly
应该
independent。
是 linearly independent。
OK，假设我们讨论 linearly
span 这
independent，
应该讨论 span， 我觉得，因为
都可以讨论，其实
都可以讨论。
你想讨论哪一个？还是两个都讨论
两个都讨论。
？OK，一个一个来。所以如果 linearly independent 的话，有想象，有情况，比如说
就是上面的
一，
对，这个样子
可以 linearly independent， 可以。
对，
但是如果这个零，
它就不
linearly
independent。
independent。OK， 看情况，可以 linearly independent， 也可以 linearly dependent。OK， 这个解决了啊。OK，我们看 span。span 的话就把这些变成任意的号码了，对不对？OK， 变成任意号码。OK， 变成任意号码，这个非常好看了。就是说，就算啊，你每一行都有一个一啊，这边肯定一定要是零，对不对？reduce echelon form 嘛。然后假设这个 b 是不等于零，你就解不了了，所以它不 span，
这就不 span，
所以就不 span， 肯定不 span。但是 linearly independent 还有可能。
那它这还能算？那还能算它的就是
不算
了？不算了。
不算。
那我就说回来的话，那有没有可能一个东西它就没有 basis 呢？因为我解出来了之后，它 linearly independent。
哎，你小心，
我混淆了。
OK， 这个东西虽然不是个 basis， 我可以把它变成 basis， 我可以再加多一个东西进来啊，我可以加0001进来，它就 basis 啊，我还是找得到，我找得到的。
随便加吗？
可以，只要你加得出 linearly independent 跟 span set。我刚才不是讲了没？你那个 n 个你随便选的，你只要是 linearly independent 跟 basis set。比如说 R2里面呢有很多个可能性的，你可以选这两个，你也可以选任意两个，只要是 linearly independent 跟 span 就好啊。很多无限可能性，其实很多可能性。
然后这个
可能我要开始啊，等下再问啊，
好，
等下再问。OK。Okay, let's finish up until 4.6, and then we discuss quiz. Okay, if after 4.6 we discuss quiz, and one thing I want to remind you, when you want to find basis, right? Basis of what vector space is very important. Okay, it's very important. It's not that I mean you need to, I mean how to say. Okay, I just want to say that if you want to find basis, you need to ask yourself basis of what subspace? Of a vector space, of code A, of null A, of row A, or anything. You need to know about your subspace first. And then ask about how to check linear independence and span in these cases. Okay, and then this question will naturally lead you to augmented matrix. Okay, yeah, it will naturally lead you to augmented matrix. Okay. But if you are advanced students, you can straight away jump to the right augmented matrix. Okay, if you can do that. Okay, if not, you just do step by step. Step by step will lead you to augmented matrix. Correct one. Okay. Okay. Right. Let's finish up these three things before we discuss quiz. Okay, so in this case here, so we have three polynomial P1, P2, P3, and then we want to find the dimension that's spanned by this P1, P2, P3. Okay, so from this statement, right, what can you infer? Actually, you can infer that the dimension of span of P1, P2, P3 should be less than or equal to 3. Should be less than or equal to 3. Okay. Because 3 vector already enough to span. So how to prove either it is 1, 2, or 3? You need to check whether they are linearly independent or not. Okay. So how to check? Set out your linear dependent relation equation, which is what? So check the C1 P1 plus C2 P2 plus C3 P3 equals 0. Okay, see if you have trivial solution or not. Okay, so go and solve this. Yeah, let's solve this together. I give you 2 minutes. Solve this. Is everyone getting this coefficient matrix or not? Expand it, huh? Try expand yourself. Correct? Correct, okay. So if you row reduce this, what do you get? Do you get something like this? Okay, if one can confirm my answer, then we can proceed. I try and row reduce it. Yes, sir. You got it? Okay. So what can you see here? If you haven't continue compute, okay, so from here, we can say that since, let's call this A has 2 pivot column, P1 and P2 form a basis of P2. Okay. So this is very similar to what we did just now for Rn case, right? For R3. So I give you 3 vector and then I ask you to row reduce it and then check what are the pivot column, right? Very similar. So what's the idea behind here? Again, like just now, your thing, right? Your thing say put this polynomial into vertical like that. Right, put into vertical like that. And then you read out the coefficient. So meaning what? You actually refer to a basis inside your P, what space is this? P2. Okay, so which is 1 T and T squared. Then your A is what? The A you see here is actually the coordinate basis for P1T and then P2T and P3T. Okay. And then you row reduce it. Okay. So the deep idea here is we are actually using the bijection between P2 and R3. So you see, you solve question like inside R3 like that. This is what we started right in the start of the class when we try to find column space. We live in Rn. Okay, so the deep idea is there's an isomorphism between P2 and R3. Bijection. if you want to think about, there's a bijection. I can go back and forward. Okay, so if you don't understand this concept, it's okay. You just go to the method 1. Okay, if you understand this concept, you can pick a nice basis and then send it to the coordinate vector. Okay, you look at the coordinate vector because the coordinate vector is this bijection. So this bijection says what? If you want to do calculation in P2, actually it's equivalent you do calculation in R3. Okay? I didn't even tell you this story. You can work out this equivalent already. Why? Just through this equation here. Just through this equation. Yeah. If you don't understand that story, it's fine. You just go through a traditional step. If you understand the story, you can use this method to get this matrix. Okay or not? Yeah. If you want to understand more, you can find me in my office hour. Yeah. Maybe we don't say it here. Okay. Any question? No question? Okay. Okay, so next one. Let H be a subspace of finite dimensional vector space. Any linearly independent set can be expanded if necessarily to a basis of for H. Okay, also H is finite dimensional and dimension H is less than dimension of V. So this says what? If you have a V, okay, vector space, and then you have a H, you can see that the size could be smaller, right? So this would implies that dimension of H is less than or equal to dimension of V. Okay. And let's say, for example, let's say R3, okay? Let's say R3. We can look at this set here. So we can say that R3 is not equal to the span of, let's say, 1, 0, 0 and 0, 1, 0. Okay, because what? You cannot create 0, 0, 1 out of these two. Cannot create. Okay, because 0, 0, 1 is inside R3, but you cannot create from the two. Thus here, true linear combination. Okay, but you can notice that these two are linearly independent also. You cannot create one from the other also. Okay, but we can extend this set to a basis. Since I cannot create you, right? I put you in. You understand or not? Since I cannot create the vector that I wanted, I put the vector into the set. Okay, so I put a vector into the set. Okay. Okay. Then it will form a basis. Okay, so this is what this theorem trying to say. Okay, any linearly independent set in H can be expanded to a basis of 4H. Okay. Okay, you can extend it until you get the basis equal to the span. Okay, so let's see. Is it enough? Enough. Okay. So altogether, we'll have this basis theorem here. So let V be an n-dimensional vector space. Any linearly independent set of n vector is a basis of for V, and any set of n vector in V that span V is a basis for V. Okay, so we are okay to prove this actually. Last time we didn't prove it, right? So now we are ready to prove this by the theorem we have seen before. For example, for part 1, how do we prove this? This is exactly the content from the previous theorem. Any linearly independent set can be expanded. Okay, expanded to form a basis. Okay, and then second, any set of n vector that span V is a basis for V. Why? This follows from the spanning set theorem we had just now. Okay, this follows from the spanning set theorem we had just now. So spanning set theorem says that if you have a spanning set, you can throw away all the linearly dependent vector such that you still span it. Okay. Yeah. So here you can use contradiction. Let's say this n set of vectors are not linearly independent. Okay, not linearly independent. So you can throw it away such that you get a Seng space. But your dimension is n, cannot be less than n. Otherwise, the dimension will decrease. Okay, so there's a contradiction. Okay, so the main point here before we finish for this part is if you know, if you know the dimension of a vector space already, for example, R3 or Rn, correct or not? Okay, so if you already have n linearly independent bases there, linearly independent vectors, they will span. No need to check one. Okay, and then if you have n vectors that span Rn, you don't need to check linearly independent anymore. It will be a basis. It will be linearly independent. Okay. Yeah. Because you need to think about it. We have a lot of choices for. Okay, let me write down some example for you. Otherwise, you think I'm singing here. Okay, so we have a lot of choice. For example, for R2, right? We can use the standard basis. Okay, 1001, or we can do variation. Okay, for example, 1011 like that. Or a lot, there's a lot. Maybe 2122. Okay, you can easily give. You know how I come up with these example? This two example case is quite easy to figure out. As long as they are not scalar multiple of each other, they will be linearly independent. Okay, so all of these are basis for R2. Okay, so you could imagine if you have n-dimensional set, then the basis, the basis could look very weird, very hard to compute. Very hard to check whether span or linearly independent. But you choose either one of them, easier one to check is enough. No need to check both. So this is the point of this theorem. Okay. Yeah, that's all. Okay, any question? Any question? You go break? Not break lah. Need to discuss. So you guys one by one come here and get maybe I call out your name. 一个, 胡一个, Chu Hui Yue. So once you take your quiz, right, please take picture first and then we'll discuss. You need to return to me before you leave. Chu Yue. Bryson, 郭琪, 雅轩, 肖雅轩, 李逸轩, 坤，你是哪一个？郭琪。雅轩、立坤、嘉伟、逸轩和逸坤都在。雅轩 ，OK 好。立坤OK 好。嘉伟，你前一个钟没有在？
哦，在的。
你在？
对，在。
我叫你没有在？
哦，那个时候我可能在上厕所。
不可能，我叫了你1个钟。
啊，没听见。
不可能，对呀，我是叫你1个钟。
我一直在那边。
OK， 下次你第1分钟就要来跟我见面。
哦，好。
郑宇，最好不要玩你的数学老师。麦一健，邱基器，哈智慧，高思玉，于子洲，孟瑞阳，开福顺，涂天天，巴杜拉曼，抓鱼街，哪个？来找一下，可以帮我绑一下吗？Nicole 雅涵、汤瑞、刘浩奇，哪一个？来，严轩、郭涵宇、黄健、孙国东、葛文业、严子轩，是葛文业，
不是，
林昌旭、葛文业，高峰、董宏伟、杨、鲁阳呢？Nicole、吕夏、俊豪、王月豪、你是这边？是月豪、陆阳、洪伟他的给他的，你是鲁阳的，你是哪？邯郸、洪泽，这你的吗？俊豪，停。张涵慈、洪泽在吗？黄云熙、林修宇，你是哪个？零。洪特哈，OK，sorry，洪特啊，洪特，我记得。星宇、沈奈、萨拉米、莫哈曼来，曹子金、海雾城、班林、喵心意、何军、郭书涵，感觉这个你的。书涵有在吗？岳阳来，班林呢？德瑜16，你算一下总分对吗？等一下，高子昭、潘泰利、俊祥、顾俊相、于泽瑞、吴浩瀚，你是谁？高子昭，来，你嘞？丁思浩，这样来。17，泽宇在吗？赵泽宇，雷乱，王宏明在吗？钟义阳，来，李媛媛，你是哪个？你是赵泽宇 ，OK。你是什么？王宏明，钟义阳，李媛媛，郭心动，sorry，刘媛媛，sorry。OK，郭心动，何瑞，刘涛，谢年佑，陈俊，邵明洲，林志俊，蒙嘉明，郑瑶。Edward，Hiba here not? Hiba not here. Benny here not? Benny here? Hiba here not here? Huh? Who? Benny? Hiba? Benny 来。魏嘉义， 百家宁、李轩、阮秋子、蒋生杰、卢星宇。This is your?
Yes, me.
Yeah. Where is Siba?
She's absent today.
Okay.
Work.
It's okay, it's okay. I can. Yeah.
No problem. No problem.
Both of them not here or what?
Yes.
Oh, both of them here. Okay, I will keep them first. Okay. I'll keep them first.
Okay.
Sure. They
Thank you,
will,
thank
maybe Friday I'll bring for them.
Okay.
Okay, let them
No
know.
problem.
Yeah. 蒋生杰、朱星宇、吴燕 is 吴燕 here? 吴燕 here 了？吴燕 not here. 林思成，来，喂，你们两个在后面，最后面。Okay, so first of all, please take photo, and then we'll discuss now. And if you think that I marked wrong or calculated wrong after the class, you should tell me. Okay, you should ask for me. And right, let's see what's the statistic before we discuss. So the mean is 73.5. Actually, not too bad. 73.5. And then quite a few of you got 19 and 20 full marks. 19, 20. So maybe let us know who are you. Li Yanxuan, who is Li Yanxuan? Okay, we got Yanxuan. Tu Tiantian, Tu Tiantian. Wow. 厉害啊。王月豪. Okay, good. Hamdan, good. Chu Huiyan, good. CME, for now, CME, account, good. Account has a very good reputation in my class, actually. My last GE batch, the top students are from account, actually. Li Xingyu 在哪里？林星宇，来 good, very good. DMT 李昌瑞李昌瑞 good. 刘浩奇 also good from finance 林思成good finance not bad Li Kun was my student before good. Sun Guodong yep. SWE also. Zhong Yiyan good. Chan Taidi yeah good. Gao Zizao yeah good. Liu Yuanyuan yeah good. Senai very good. Okay, that's all. So I call out these names. So if you want to get help, you can ask them. Okay, so you can ask them for help. Okay, so let's discuss. One thing I want you to do is, if I don't discuss about your answer, right, you can shout out your answer actually, because I cannot cover everyone's answer. I just write one or two answers I can think of. I'll let you know what I meant. Okay, so first question is very straightforward. You just do row reduction. Okay, row reduction has an algorithm I teach you, right? So what to do first? You find the leftmost pivot first, okay, from any row. And then after you found it, you should make everything below it become 0. And then find pivot in the second position, okay? And then make everything below 0 again. And then until you find the last pivot, okay, the last pivot. Okay, and then you start making 0 above pivot. Does it make sense? Okay, I think about 1 or 2 of you are still confused about row reduction. So please follow the algorithm. So how do I give marks? So as what I promised you, final answer only 1 mark. Okay, if you manage to like reduce to the right IEF, okay, this part wrong, I deduct 1 only. Okay, I deduct 1. And then the step here depends on which part you go wrong. If you go wrong too early, then you will get less. If you go wrong to like last few steps, then you'll get a bit more. So in this course, right, I want you to focus on method, how to solve. Again, not calculation. No calculation. Calculation is not too important here. Okay, maybe in your field it's very important. For example, account, right? You cannot get your account wrong, right? Otherwise, you get fined. No? Okay, so method is more important in my class. Okay, so far okay or not for this question? Everyone okay? Any question on this method? Yeah. All right. So next part. So this part, I want you to write down the associated linear system in 1 and x solution here. So a lot of you just write down the linear system that you get from the last one. Last REF form here. Okay, but this is not what I wanted because I asked you for this part here actually. Okay, associated linear system, because this make more sense, right? Because what does this reduced row echelon form do? Okay, what does this augmented matrix do? It translates a question from a linear system here and then solve it for you. Okay, so this is why the question, how the question come out. You get the linear system first, and then you get out the solution. And then this solution, I want you to write it in a parametric vector form. Okay, I think about 1/3 of you still a little bit confused about parametric vector form. Either you just write this part without this part, and then either you read it wrong. Okay, read it wrong. Okay, so but even if you write down the associated linear system for this, I still give you 1 mark. Okay, I still give you 1 mark here. Because at least you know that augmented matrix can be translated to some linear system. Okay, so you're given 1 mark. And then okay, so depend on what you get from the question 1, how you read from the question 1. If your question 1 already wrong, then your question 2 answer based on question 1, I still give you full mark. Okay, based on what you have before. Does it make sense? Okay, yeah, depend on what you have before, I can still give you full marks. Okay, yeah, because these questions are connected. So if you wrong one, then you have the chain wrong, or then you will lose a lot of marks. So instead of that, we will do something called ECF. We will call it ECF. Error carry forward. Okay, based on your error, then see what you get. Okay. Okay, third question here. Determine whether the set of vector is linearly dependent or independent, anything, anyway. So what do you think? What should you do? Edward, what should you do? What should you do? Okay, continue. Okay, good. So you use theorem also. The number of vectors is more than the number of entry. 4 greater than 3. Some of you just say P greater than N. I don't know what P, what N. Right. You should say that the P here is 3 and then N here is, sorry, P here is 4, N here is 3. Right. So 4 greater than 3. Otherwise, what is P, what is N? I don't know. Okay, you should say it clear. Anyone solve from definition? Anyone? Who? 忘记了什么名字？心怡来，你做什么？ What did you do? Okay, so you set out a linear dependent relation between these 4 vectors here. Let's say V1, V2, V3, V4. So C1 times V2, V1 plus C2 times V2 plus C3 times V3 plus C3 plus times V4 equals to 0. And then show that C1, C2, C3 has only the trivial solution. But if you do that, did you realize something or not? Did you realize anything? What did you realize? It is the same matrix you're going to get from the first question. I'm very shocked. Actually, most of you didn't realize it. Why? You know what do I mean? Because in your mind, right, I gave you an augmented matrix. You should have a fixed algorithm to row reduce it. So let's say you met the 2 matrix in different places. I think your algorithm should work the same, right? then you should realize that, hey, seems like I do this sequence of row reduction before. This is how you like test whether you see these things before or not. One thing I can imagine, one possible case I can imagine is, even if I gave you the same matrix, you might row reduce differently for me. So that's why it's very hard to track whether you see this matrix before or not. Okay, this is one possible case I think about. The other possible case, maybe you are not sensitive to the row reduction. You are not sensitive. So you just plainly do, like robot, just do. Don't know what you are doing. Okay. So I want you to know what you are doing, because if you know what you are doing, you will save yourself a lot of time. Okay. Yeah. Okay. So let's see. What do we do here? So I assemble them. I go advanced a bit. So straight away form this matrix and then row reduce it and then check that it doesn't have pivot in every column. Okay? So it has in particular, it has a free variable. Okay, so this is a free variable way to solve it. The other way is what Edward says, use the theorem. Number of vectors is greater than the number of entry. Okay, yeah. Any other method you use that I didn't list here? Any other method? You are different from here one. Anyone? Do you have any other method? I will post this to the Moodle also later for you to refer. Any method? Other method? No? What time is it? Okay. So let's go to the last one then. Okay, so to the last one. Wait, anything I want to say? Oh, yeah, there's one thing I want to say here. Okay, so this is the place where you get this one not equal to 0. Okay. Some of you because you want to solve this augmented matrix with 0, 0, right? You say that 1 is not equal to 0, so the system is inconsistent. Can I see who did this or not? Who did this? Can you admit yourself? I'm not trying to laugh you. Anyone do this? 1 not equal to 0. Yeah. 不是 okay. Any one of you? Okay, if you don't want to admit, it's fine. But I want you to listen carefully now. Sure, 1 is not equal to 0. But this is not how you read this. How should you read this? How should you read this? This is C4 equals to 0. This is the coefficient for your variable. Okay, so this is concerning on the parametric vector form already. Right, parametric vector form. So what's this parametric vector form? So C1 plus 4C3 equals 0. C2 minus 4C3 equals 0. And then C4 equals 0. So the parametric form is C1, C2, C3, C4 equals to C3 times minus 4, 4, 1, and 0. Okay, this is the solution. Okay, this is not what you read. It should be C1, C4 equals to 0. Okay, so this is wrong here. So this part is wrong. Okay, so instead what you get is, so from this line, you should get C4 equals to 0. Not 1 not equal to 0. But, like, okay, so example, yeah, but why here is 0 not equals to 1 here? Because if we have C1, C2, C3 here, what we have instead is 0 times C1 plus 0 times C2 plus 0 times C3 is equal to 0. That's why you got this 0 equals to 1 here. Okay. Understand or not? Okay. Okay. Okay, so please be careful. The 0 and 1 swap is a different story. Okay. Okay. Okay, next part. Last part here before we go back. So let's consider this transformation here. Linear transformation is a matrix transformation because you take a matrix times vector A times X. So does T max onto R3, okay, or is T one-to-one transformation, okay? So from definition, right, this is what you need to do, right? Okay, for any B1, B2, B3, you need to find it. Okay, but what is this, huh? Solve the augmented matrix. Solve the augmented matrix, but this is the same augmented matrix in question 1. Okay, so in question 1, you dig the REF form. You should take the REF already. Okay, you should take the REF from the question 1. So to see that the system is consistent, what do? You need to check that every row should have a pivot. Okay, you should check that every row has a pivot. And then to check that it is one-to-one, you need to check that every row, every column has a pivot. Sorry. Yeah, every column has a pivot. But in our case, we have a column that cannot have a pivot, right? Okay, so that is a free variable. Okay, so what am I talking about? I'm talking about this this last part here. So let's move this. Let's copy here. Okay, so if you look at this REF here, so let's write down here REF. We can see that there's a pivot in every, not in every column. In particular, let's call it S3 here. S3 is free. Okay. Anyone of you solve differently this question? Yeah, some of you solve differently. What do you do to show it's not one-to-one? You produce two solutions to the same answer. For example, there is another vector that map to 0, non-zero vector. Non-zero vector. Who did this? Can you tell me what's the other vector that sends to 0? What's the non-zero vector that gets sent to 0? Who did this method? Who? No one admit 了。有人吗？有人用吗？有人用另外一个 vector 送去0吗？没有人咩？ Who Hey, hello. Here got like about 87%. Oh. Did you find another vector that gets sent to 0? Anyone of you? 没有啊？你 Yeah, 来给我 -8, 8, 2, and 0. How do you find this? Wait. Let me bring this part down. Okay, I want to show you that all these questions are connected, deeply connected. Okay, so in our case here, right, our B are all zeros, right? Okay, so this constant vector part will disappear. So you take x3 equals to 2. I think one of you take x3 equals to 1. So you also can compute t on -4, 4, and 1, 0. It should compute to 0. Okay. Okay, one myth here, on two, a lot of you, I think, panic in the exam. Okay, so what you do is you just give x1, x2, x3, x4, and then you multiply it out. And then blah, 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 x1, blah, blah, blah. And then you say that this one live in R3, then so it is on 2. Wrong. Wrong. Not like that. This just says that it maps into maps into, so here you got R4, right? And then here got R3. It just says that you map into, you are not onto. Onto meaning you need to hit everything in the target. Everyone you need to check. You need to hit everyone. Okay? If you just do this, you just say I land in the right place. That's all. But onto means what? You need to onto everyone. Everyone you need to hit one. So that's why when I set out this equation, right? B1, B2, B3 are random one. Check for everyone. Random. Okay? Yeah, so there's a very important concept here. Onto meaning you need to hit everyone. Okay, if you just compute like this, it's just that, okay, good, you get the right vector. It's in R3 already. But onto it, right? You need to onto it, onto everyone. Okay, you need to check for everyone. Okay, yeah, this is the main mistake I see. Yes. 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 Okay, good, very good. So again, come from here. So how it helps, right? So you see, in our REF form, right? In this case, we let B1, B2, B3 as 0. Correct? So in this solution here, it says that S3 times this vector will be living inside your null space. How to verify this? Take S3 to be any number. Either 1, 2, then you will get, if for 2, you'll get this minus 8, 8, 2, 0. And then 1, you'll get minus 4, 4, 1, 0. And then go and multiply with your matrix here. You'll get a 0 vector. So, meaning what? The solution to a homogeneous system isn't just the trivial solution. Has more than trivial solution. Yes, it's not one-to-one. That's right. Correct. So for linear transformation, right, you just need to check the image, the pre-image of zero vector. Yeah. Okay. Yes, that's right. Any other question? Any other question? Any other question before we finish? Okay, so if you have problem with your mark, you can find me. If not, you return your quiz to me because the school need it. Hard copy. Okay. Because okay, right. But here you haven't REF, right? It's okay. What do you mean by it's okay? No, it's not okay. It's not okay because this is not REF form right yet. So yeah, so you actually haven't completed your step. Yeah, I know you compute wrong, but you haven't completed your step yet. Yeah, do you know that? Yes. Yeah. So you should do one more. If you do one more, then I'll consider this is just miscalculation. Otherwise, I don't know whether you know what is REF form. Okay. Make sense? Yes. Yeah. OK， 它的定义就是说，每一个这里的东西都有一个这里的集，每一个 R3的东西 ，OK， 都有一个 F， 都有一个 R4 东西。这边，你写。每一个 R3的东西，你都会有 R4 的东西 ，such that 这个 matrix 要等上这个 R4 东西过后就是说每一个 R3 里的东西都有一个 pre-image， 都可以找到。
每一个 R3 里面都有一个 pre。
对，没有错。因为我要 hit 到每一个 target 里面的东西，或 domain 里面。
我能这样理解，我不懂啊，
你想想看的，
就是来这意思讲话，其实我因为有4个variables， 其实4个嘛，所以就是我最后找到答案是3个 solution 这意思。
这个只是这个 transformation 在做的东西，但是等一下，
我那个在上面订正了那个
可以吗？我就拿铅笔订正了刚才，就是还是要我擦掉。
什么东西？你说的？
我刚才在讲课的时候拿铅笔订正了一下。
如果在 quiz 时候没有出现这种东西，就要擦掉。
那我回去。
你擦掉，你擦掉，你擦掉，不要写东西在上面。
好，
这3分是谁的？
这是我帮同学交的。
哦，你帮他们交？
我帮他们交。
可是他们刚才有在不是？
有在。
有。OK， 你刚才说什么？
对，交流啊。
每一个 R3的东西都有一个 preimage。
这个 R3是什么东西
？R3就是那个 vector，这个 vector， 就是对这个东西你一直不了解哦，感觉这个 Rn 你一定要记得，这 Rn 里面长怎样，就是 n 个 tuple 的东西。
Professor.
Yes.
Just about the attendance. Do I need to wait where I go?
Okay, you can go. I have a way to like detect all of you already.
Okay.
Yeah. Okay.
Thank you.
Just 3 didn't come today.
Yes.
Good. Good. So R3 的话就停在3个咯 ，S1、S2、S3。这样子。OK。所以你看，就3个东西哦。
这3个不是它的 solution 就是它的答案总会是。
你要把它想成 solution 也可以，但是我想一下啊，为什么你叫它 solution 呢？给我想想。不用紧，我知道你有来。我会点你来。
如果有一个 equation 是来 x 啊 ，x 这个是我们的，比如 OK， 现在我们的 x 等于1，OK， 这个 x 等于1是我们的属于我们的这个 R4 的其中一个 R1，我把这个1放进去，它就变成这个 R3。
不是，喂，给我想想，
这个就是它的 image 嘛，我的答案就是我的 image 嘛，我放进去都没。
OK。这个东西是你要放一个4个东西的 vector，4个号码的 vector， 它会吐出一个3个号码的 vector， OK， 然后你要什么？
就是我是不理解，这是所以，
就是这样啊，这个是这个，然后你要理解什么？
就是什么是 maps T R4 to R3，其实
对，所以说这个的 map 的方式的意思是什么？就是给你一个这个里面的东西 ，OK， 然后你用 T 作用在它上面，你就得到一个 R3 里面的东西。然后继续。
这样解释要怎样解释哦？
解释什么？你要解释什么？
我能这样解释吗？我
不是啊，你不是要做这个事情啊？问题是你不是在做这件事情啊？你的问题是 onto 的事情啊 ？onto 是什么东西？
进去还是上？
不是进去吧？你要进完所有的地方，你不可以进去吧？这个就是刚才我讲的东西，你不可以进去吧？你要动到里面所有的东西。的意思是什么？每一个 R3 里面的东西都是从 R4 来的，都要有一个 R4 的解，对吗？讲一下。
这个 R4 是我的 dimension。R4 嘛
，R4 的 dimension 是 4， 然后
R4 dimension
啊又怎样？
在这个在四维世界里面，我们里面有很多东西，
然后
拿出来，这是我每个3维东西在4维东西在4维里面的意思。
我不觉得你可以这样想，我不觉得你可以这样想，也没有必要这样想，没有必要，这个就很字面上的意思罢了。
就是重点拿分数，是哪一个重点拿分数？就是要写到什么东西就可以拿分数。
定义咯，定义这一行。
重点是这个 B1、B2、B3 啊。
No， 这整句话都是重点，整句话都是重点。每一个这个都要找一个 x，such that 这个是对的，明白吗？
就代表 B1 里面一定有 x1、x2、x3、x4 啊，
可以把它乘出来。
明白。
这整句话都很重要，这整句话很重要啊。它的重点就是不是进去罢了，你要 hit 到每一个人。 踢到里面，yeah, 不止进去，yeah. Okay. Yeah.
Why is it wrong?
Why is this wrong?
I have a diagram from textbook.
未来，我们谁来的？ It's not wrong. It's not wrong, but I think it's not wrong.
So it's considered correct.
Yeah. You didn't change anything, right?
Yeah, I didn't change anything.
Yeah, nothing wrong actually. Yeah, nothing wrong actually.
Another thing, this one is I expect that this need to write in parametric vector form.
Correct. Parametric.
But I thought this associated linear system need to write in parametric vector form. Because this is what I understand from the question.
I mean, two parts, right? Based on this thing and this thing.
But this one both need to be in parametric vector form.
No.
From what I understand.
No.
No. Because this got n here.
I mean, my n. I mean, you can read like this one. Right. Correct. I mean, we didn't define parametric vector form for associated linear system also.
This is not parametric vector form for linear system.
Let me think. No, this is what we call a vector equation. This is what we call a vector equation.
Okay, so you add up the marks, right?
Yeah, I will add up the marks for you.
Okay.
2 marks, right?
2 marks.
Or 3 marks. Okay. Yeah, why I give you wrong? Okay,
thank you.
Okay. OK， 给他们解决亏先呢，我再解决你的。OK。
我发现我这个答案为什么会扣2分？
你的答案
就这个是因为封面不对吗？
对，没有错，封面。然后是你是说没有？哦，你把全部挤在一起啊？
对，就是
对，封面有问题，因为我们要把那个 parameter 拉出来，那个 S 单要拉出来，要，That's yeah。这个就有 vector form 吗？
OK， 这是因为就是这个 X3 is free variable，不能证明它
不能，因为你要 make sure 它 consistent。它 free 它可以不 consistent， 你这边可以变成0。
这样子
啊。
就是到这里这样子写还是不可以，因为 x is free， 那肯定 t(x) 等于0，肯定就不是唯一解了。为什么这样还不能证明？
因为你没有写理由，所以我不知道。
就是t(x) 等于0，然后 x is free。
对，我知道，就是说怎么说呢？对。
这样可以加1分，因为我这个真的知道。
什么？
可以加1分吗？
然后
这边不是2分吗？
对，没有错。想想。要 one-to-one solution。
Not only solution。
下次你要把这个理由提出来。因为
确实，因为考试的时候可能比较紧张。
可以，但是我就说下次你要记得提出来，因为不然的话，如果下次改错，你就检查不了。对，加1分。OK。好，对。还有其他问题？OK，特餐。OK，等一下。
排到这边来，他这边是课上的对，这个是卷子的对。
先把那个 quiz 解决掉，来。
each column 0。
确实是错。OK。OK。
OK。
然后我扣你分了。可以啊。
扣一分
OK 啊，扣一分吧。可以。
但如果它是每一个 row 都有的话，就讲 row，然后如果它是 column 的话，才讲 column。
什么意思？
就是因为 pivot 是 leading one 嘛。
对。
所以如果我这里还有一个 leading one 的话，那就是 each column 就对。
肯定。OK。但是你是那时候是写错还是？
我写错。
想错。
我写
错吧 ？OK 好，没事。
你不要扣。因为我真的是写错。
我知道，我可以都
我是分2分钟的时候，我才看到后面还有一题。
OK，可以。
我就紧张。
OK，我改，可以谢谢你。
我改什么？
你不是说我扣吗？要扣啊。OK，I mean，1分就0.5分嘛，对不对？OK，不要扣。
就是1分啊，总共。
没有啦，扣1分吧，扣1分吧。因为你有做这一个嘛，但是你也没有做在 B1、B2、B3上面，是不是？怎么你写2次同样的东西？
因为我就是紧张了，然后我就没有想到这里是 B1、B2 那些。
OK。
跟姐你扣啊。可以的，0.5分吧。
没事，你 final 不要错就好。OK， 好。
我这分是不是加错了？
啊？
我这5分、4分和4分，你给我写的少了。
哦，少了几分？13分了。
对，
少了1分。OK， 好，可以，谢谢。
他说还是不理解这个 basis，你说这个题吧，就你刚刚上课讲到这里，说 P1 和 P2 form a basis of 这个对吧？然后就像下面这个的话，那001就是001，我谁来提供呢？就是咱们这个不是也是说它不算 span，它是因为没有人提供001，所以我们加一个001进来吗？
你要提供这个哈？
对啊，
提供哦。
可是您直接说 P1 和 P2 form a basis of P2 啊？
哦，喂 ，sorry， 我讲什么？我在做梦哈。哦 ，OK， 我都告诉你了咯。你要看一下他问什么问题。他问的问题是 dimension of subspace spanned by 这3个东西。所以它的 dimension 只能够是小于等于3吧。然后我在这3个里面去找谁是 linearly independent 的东西。很少只有这2个是 linearly independent。你如果不相信我，你可以去找一个，你可以把第3个写成这2个的和的 linear combination。
我明白，所以但是它 P 这个东西的 basis 它不应该是只有 P1 和 P2。
对，没有错，所以你写错了。这是 basis of the subspace of P2，不是 P2，我写错是吗？是我写错还是你写错？我写错是吗 ？Sorry， 我有写错吗？没有，题目是 dimension of subspace of P2，不是 P2。我写错是吗？还是你写错？检查一下。
可能是我写错了，我觉得。
我也有可能写错吧。但是你有看到吗？你有看到题目吗？
我看到的
dimension
of subspace of P
是某个 subspace of P2，不是 P2 本身呢。我写错 ，sorry， 是我写错。
还有这个，就是包括这个地方，就是 row space 也是一样，就是找那个嘛。然后我还是说，为什么它这个00010和00010也没有人提供为什么 basis for row space A 就可以是这个？
因为他们第一个它
independent，
对，没有错，他们linearly independent 对。
可是就是这个 basis 不是要满足2个条件，一个是 linearly
没有错，
一个 span，
没有错。来 span 在这里啊，你自己写了 span 了，你写了。
row A 不是等于这个的 span 吗？
对呀，没有错啊。所以它的 dimension 肯定是小于等于4嘛。
天哪，听不懂。
不是，你讲为什么这个是等于哈？
是小于等于，就是它的 dimension。因
为刚才记得我们说嘛，如果你有一个 spanning set theorem， 你有 span 的话， 你可以把 linearly dependent 的东西丢掉。
对
对，所以所以丢掉过后，你的号码就变小了嘛，所以是小于等于哦。但是有几个 linearly dependent 呢 ？Obviously 这个肯定是 depend on 其他咯，所以我先把它丢掉，那我就去检查剩下3个咯，检查出来哦，原来他们确实是 linearly independent， 所以它又 span 又 linearly independent， 所以就这3个，对不对？没事，慢慢来。
我不明，我还是不明白，就是
没事，你讲你不明白的地方。
老师是不是因为就是这个 row space A 这个地方也不需要用到就是这个00100和00010这几个，因为我只是 span 这一些。
对呀，
我
对呀，没有错啊。
就是他用不到这2个，
对呀，
所以
不一定用得到，我也不知道用不用得到，不一定用得到，不一定，可能要，可能不要，我不懂，也没有检查过嘛。
那如果用得到的话，那我没有这2个，那这个 basis 不就不 span 了吗？
没有，你要看这里 ，row A 本来就是天然
等于这个的 span，
对，没有错。
所以说明不管我解出来，不管我 reduce 成什么，它这几个都是 span 的。我说了什么？
你再想一下，可以再问的。
我没有理解，但是我知道应该怎么做那个题，但是我还是想理解一下，但是理解不了的话，其实也没什么太大关系，我觉得其实。还有一个就这个地方，这个。不着急。
OK，
然后这个 dimension of column space A，
对，
然后就是这个指的就是，sorry 老师，就是 numbers of 那个 basis 里面 vector 的数量 column space 里的，
没错。
所以就是说，如果说我有一个，比如说我有一个这个东西的话，然后我 row reduce 完了之后，然后比如说这有3个 pivot，那也就说明它的这个dimension of column space 就是3。然后剩下的2个就是它的那个 non space 是吗？
没有错。如果你把它的那个parametric vector form 写出来啊，这2个答案就是会解。
我知道会有一个 x 什么什么
x 会解
3
ax 等于0，会解 ax 等于0。
对 ，OK， 我明白了。
没问题。你们是同学？
不认识，但是我觉得我也没怎么听懂，它太抽象了。我觉得就是这个 non-space vector 了之后，我觉得
OK 有一点点
抓不到题目。
之前这个 R 它是表示是几维的空间吗？
对
，x y z 的话那就是3了。那在这里是2，是不是因为它永远有一个常数项？
不是，
还是
2是这个，2是 at most 2 degree at most 2这个2。
哦，是这个
at most 2 degree at most 2。
懂。
所以刚才说它的 dimension 是 n 加1嘛，因为加了这个1嘛。
n 加1。
对，刚才我不是说 dimension of， dimension of p n 等于 n 加1嘛？一项2项还有一个加1。
懂了。那我懂了。
OK。
谢老师。
谢
谢老师。
OK，thank you。
这周按照计划应该只考 Chapter 2。
Yes。
谢谢老师。
可能我等下再发一下那个通告了。好，拜拜。